My name is Amit Ashbel. I work for Checkmarx. Shimi Ashkenazi, he also works for Checkmarx's research team. We're going to talk a little bit about serverless injections today. Serverless is a big thing now. It's growing significantly, and we thought it's important to look at the security aspect of that. How many of you, by the way, are using already serverless? Okay, nice. Like 10%, 5% maybe. So we'll quickly talk about an introduction to serverless, which I'll run through very quickly because most of you probably are familiar with it. We'll look at a few serverless security assumptions, and then Shimi will have the hard work of doing the demos and explaining the technical details of what we did in terms of understanding where the security is limited, what needs to be improved, changed, or what's good also. And then we'll have an example of what you can do in order to test your security or your code security even in a serverless environment. So starting off, in the past we had data centers. Hardware was the unit. The abstract material was actually the physical hosting environment. So you had a computer, a server in a hosting environment, and that was your server. Later on, we moved to infrastructure as a service, where the operating system became the unit of scale, and the hardware was no longer relevant for the, let's call them the users, for us. And then we had platform as a service, where the application was the unit of scale, and the OS was no longer relevant. You just launch your application, it runs there. You don't care where it's really or what OS is really running it. You don't have to set up an OS or anything like that. And today we're at serverless, where function is the unit of scale, and the language runtime is the abstract. There are a few different types of serverless environments today. There are more than these. We'll talk about them also later. AWS is probably the main one at the moment. We then have Azure, IBM Cloud Functions, and Google Cloud Platform. We'll be talking specifically about AWS today. So again, looking back, data centers we used to deploy in months. So you had to set up your server, implement it, make all the security checks, and so on and so forth. And then they used to live there for years. Later on, we moved to deploying in minutes on virtualized clouds. And the systems used to live for weeks. They still do. And when containers were introduced, we deploy in seconds. And we live for hours. So you drop the container, you start a new container. And with AWS Lambda, you actually deploy in milliseconds, and you live for seconds, actually 60 seconds. After these 60 seconds, the functions that you've deployed just disappear off the server. So again, the classic approach, you had the backend, which was stateful, very accessible for hackers, where today you actually don't really have a backend. It's not stateful, at least. You do have a backend, but it's not stateful. And it moves all over the place. So one of your functions could be running on thousands of servers at multiple time and disappearing, or running on a bunch of different servers and replacing every time. That's the process. You develop, you push, you trigger, and you clean. So nothing is left over. That's the assumption, that nothing is left over after you finish deploying your functions, or triggering your functions, actually. The advantages of serverless infrastructure are, one, that they are scalable. You can run as many functions as you want on as much CPU that you want. There's no operations behind the scenes. It's very easy to implement. And the cost is lower because you're only running what you need, really. You're not buying a server. You're not buying a cloud server. You're actually running exactly what you need, or leveraging the CPU and the resources that you need exactly. The disadvantages, first of all, it's a new paradigm, like every new paradigm that has to be learned, understood better. It might be a bit slower in some cases because you have to trigger or start the function every time. That might take a few milliseconds. Monitoring is difficult, again, because you're not really sure where your functions are going to run at any given time. And it's not platform dependent. So you have, as we said earlier, you have the different vendors who provide the different platforms. So a little bit about the different platforms. We mentioned the commercial ones. There are also some open source solutions, quite a bunch of them actually. Here are names of some of them. And this is an overview of the top three. AWS Lambda, it's probably the most common and mature. As I mentioned earlier, it's been around since 2014. It has a wide language support, or wider language coverage, and we'll focus our demo on that specific platform. And then you have the Google Cloud function, which was introduced about 2 years ago in alpha. It's still considered in beta, and it supports only JavaScript, Node.js runtime at this stage. Microsoft Azure, also introduced 2 years ago, supports a bunch of languages in experimental stage. Very well integrated, obviously, with Visual Studios and Microsoft environments. A bit more about Amazon. As we said, introduced 2014, supports Node.js, Python, Java, Go, NetCore, Linux containers. Can be triggered using all of Amazon's different services. So whether it's S3 or any of the services that we use on Amazon's AWS. Obviously, you also have an API gateway that you can leverage. Well, this slide talks about the different use cases for serverless environments, but I think that the most relevant ones would be the file and image processing and any heavy CPU utilization. So imagine you want to do image processing today, you need a lot of CPU power. If you want to do image processing with serverless, you just need a lot of servers running the same functions or the different functions. So it's very useful when we're talking about high CPU or CPU-intensive functionality, which includes a lot of these specific cases. Some assumptions based on a research done by Rich Jones a while ago. So the fact that the functions are running in their own environment reduces the potential damage, and the fact that nothing is stored, so the function is removed, deleted, disposed after run, also prevents stored injections, because if you inject something, it's deleted later, the function is new and clean, should be much more secure. With that, I will pass it on to Shimi, who will show you why these assumptions are not necessarily accurate.
Thanks, Amit. So as Amit mentioned, the common assumption is that the serverless is more secure than others. Jones and other security researchers, including Checkmark's research team, want to eliminate this assumption. So in the research team of Checkmarks, we wrote a demo app that has a simple UI, and in its backend, it's run three serverless functions in the AWS Lambda. Here is an example of two functions. The main function is invoked once this page is loaded, and it's returned as the results, the data of the main box, including the visitors counter. And inside it, it's invoke another Lambda function called cars, according to the marked input in the URL, cars, and it's get a parameter, a numeric parameter 1, and in this case you can see the front end of the application, including data from two Lambda functions. Another function in this demo app is the users, and again you can see an image of the user, the internal data taken from a cloud database, and there is a really thin client that only invokes serverless functions. And let's see it's running, just to be sure it's not a screenshot. As you can see, while it's loading, there is the invocation of the Lambda function. In this stage, the container is triggered and created, and in milliseconds it disappeared. It's for the user side, it's like any other application. So this code that I wrote, secret, it's include code injection. After all, code is code. It's every code, if it's written correctly and on purpose or not on purpose, could be vulnerable. What is a code injection? There is a very basic definition of OWASP. I'm pretty sure you already know. In case you have an input that's it's sourced by the user, it's not being sanitized, and it's get in the data flow to an invocation command like evil in JavaScript, then it can be harmful. So here it's the code that I wrote, and I on purpose entered the code injection inside it. You can see an eval of the JavaScript that's running the code, and the code is built of the event trigger. The event trigger is the input of the Lambda function. As we said, event trigger is not always a text box or a regular input. It could be IoT button, it could be API service, and in this case we could include two parameters that we saw in the URL. The resource name that will create the invocation to the internal Lambda function, and the number as a parameter. So, okay, this is the function code. Beside this marked code injection, you can see in this, I admit, ugly code, another vulnerability. It's marked in the first line. There is some sensitive data exposed in the code, not related to serverless, but just we'll get back to it later. If you're writing your code, don't do it. It will have a serious impact in the next stage of the demo. You can see the database call, including the API key exposed and not scripted in the code. Okay, so assuming we have the code injection, and we'll try to attack it with fuzzer until we find the malicious inputs that will do us harm. What can the hacker do? Which info there is in this no server container? Okay, so I read the Amazon documentation, and I found this container contains some environment variable. One of them is very interesting. It's the path of the Lambda code function code itself. So, assuming we know there is a code injection in the function, and assuming we found after brute force the malicious inputs that can invoke this eval, and we try to get this info from the environment variable. And especially we want to be focused and get the Lambda task root. Let's see it in demo. This malicious code on the same URL. And we can see the result is var task. It's not surprising. It's the default location of path of the code in Lambda containers. So we have our demo application, and we know it's on demand. It's create a container that's contained the function's code, and we know where it stores in this container in the specific folder. And as an hacker, outside of this environment, I have several of my own. Using this code injection, I want to check, can I copy this code to my location as an hacker or not? There will be, I assume there will be some block of limitation in the network that prevent me from doing that. But I was surprised, and it was not. Here is the malicious code I wrote. I'm using classic libraries available for Node.js. I'm zipping the source code that I know where it stays in the var task, and I'm sending it to my hacker server URL. Using a non-common port, it's also an int that will get back in compared to other solution. Here is my server of the hacker. Currently it's empty, running this malicious code. And let's see what happens to our server right now. We can see a copy of this zipped source code, and let's see what it contains. It contains the code itself, including the sensitive data that was exposed in the code. And another thing, even if it was not in the code and it was in the configuration beside it, we could get it as part of the zip. But it would be a bit harder. Here it's obvious. In the code, you can see the hard-coded API key that could be used by this CloudDB, but you can be, no worries, we already replaced it since then. So we done a simple code injection, but we don't want to do some more complex and advanced actions, not just copying a code. What tools do Amazon give us? So Amazon have an SDK that can do some cool stuff with Lambda. It could get a list of all the functions of your account, deploy it, and invoke it. It's usually useful in the development environment. And when you're doing it in your development environment, you are authenticated by your AWS profile, and you can do only what you are permitted to do. But what if you're doing this using the same SDK that it's already built in the Lambda function, and you're doing it, calling it within the Lambda function itself? In this case, there is no authentication. Amazon counts on the settings that were set in the predefined Lambda function, including the execution role, and only what the execution role that was predefined for the Lambda can do, the same action will be permitted by the SDK. So I don't know what permission do I have, so I try to write this bit more complex code, including using the AWS SDK and using an update function code. Update function code will create a stored injection. It will rewrite the original function and will edit some malicious code. So here we see the original output of the both functions. It's clean as we saw it before, visitors and details. And here is the original code, nothing suspicious. Now I'm running this malicious code, including the AWS SDK usage in the and including the update function code in the end of this URL. And once it's done, we come back to the application. We can see that the result of the output contains some strange output, main act by CX. What is written there? Let's go to the main function, what's happened. The hacker gave us a hint. He marked this function as act, like a good hacker, and he's also added this malicious output in the result of the function. And all this using the AWS SDK of the within the malicious input. Okay. So this was a stored code injection, not a regular. We used the permissions that's given to the execution role of the function. But again, it was a one-time damage. We can reset the function, and it will go back to the original code. The code injection path will stay since we didn't fix the problem, but we can control on the damage. Let's see, in this case, both functions were infected, both the cars and the main, and you can restore the cars to the original code, assuming a DevOps doing that. In this case, the cars was cleaned, the main was not cleaned, but there was no impact since the main only was injected and was not viral. It does not affect on other function. The isolation of a AWS Lambda was useful in this case. But what if we want to do some more hard damage that is harder to fix? In this case, every stored code injection will not just add some output in the end of the JSON, but also infect all others it has access to. In this case, you are going to get a cross-contamination that is in an endless loop, will inject all other functions that get useful, and you get out of control. Here in this our case, we have 3 functions. In the beginning, they are all clean. We will inject only the users. We'll run the cars and the main, and we'll see they are both clean. We'll load the user functions. We will see the contamination and all the systems got infected. We'll clean the main and the users. We'll see they are both clean. But when we load the cars that was forgot to be clean, their system will be damaged again. And the only way to get out of this situation to be to reset all the functions to the original source, but all of them, without forgetting any one. Here's the scenario. In the beginning, it's all okay. In this scenario, we can see some small lag because the function code is being changed every time, and the caching mechanism of Amazon needs to re-trigger it cannot restore the code from its previous version. And especially all the infection and contamination takes some time. But as you see, as we described in the scenario, the cars was injected, and is now contaminating the other functions. Both cars and main are infected, but I'm cleaning the main function. and cleaning the users. The DevOps do it. They think they got control of the situation. Everything is okay. But when it'll go back, some other user will run the cars function. It will infect the car function, and in the second run, we can see that the main end user got infected as well. Okay. So how can we prevent such attacks? There are two main layers of protection in the AWS Lambda that should prevent it. The first one is the execution role. The Lambda function can only do what it was meant to be done by the execution role permissions. And luckily, the default is the basic limited permissions given set by Amazon. In this case, in this demo, I on purpose changed the role to a full access control. And you could say it was a mistake. I'll show in the next slides why this mistake is not so surprising. Another layer of protection is the VPC that should isolate the container and prevent outbound connection, but unfortunately the default was no using VPC. So we talked about the execution role. There is a long, complex documentation on Amazon that if you read it very well, you will not do it. But assuming you are lazy, and you are, well, let's use some open source tool that's make our life easier, deploy Node.js easily to Amazon Lambda, found at Google, and very common open source framework. Let's see what it says in its documentation. Oh, it will require AWS Lambda full access. Not so good. Once you have such role in your system, you can get easily confused and use as related privilege. But you say it's just one tool. Not everybody using it. But I'm sure that Amazon are responsible and not having such cases. So again, you can be a good developer and in all the documentation, or you're lazy. You just Google for ready code examples. And while you're looking for a ready code example, but official one of AWS Labs, not someone wrote in and uploaded. So the official code example of AWS Labs include the following comment. Assign AWS Lambda full access. Not good. So this is all about how we can get confused and create the AWS Lambda function, AWS Lambda full access permissions to your execution role. And here again, proof that the VPC on the other end, it's more easy to get confused because the default is no VPC, the first option. So these two layers of protection that were meant to protect us. One was easily hackable with no VPC by default, and what was easily to get confused by using external tools or using a wrong, obsolete source sample. But what is the lesson of all of this research? That there is no such thing or cloud or serverless. There is always someone else server that you should be worried about and protect it. There were at least two servers. The servers that's containing the temp container and the servers that's containing the source code. In Amazon, it's probably S3. And code is code. And if you not write sensitive data in your code in the server, the same way you should not write sensitive data in the serverless code, since it could be exfiltrated and get stolen to the hacker server. You should be aware in this case of Amazon that the AWS SDK is built in the Lambda container. And you should be aware that the VPC must be defined, otherwise the default is open. There's a good reason that there is no VPC for easier common use cases of getting data from the internet, but sometimes you should get control of this isolation. And beside the fact of the AWS SDK is built in, you should be aware about its execution role effect. In most cases, the basic limited permissions are good enough. If not, you should control and read very well what are the permissions you are giving to your function. Since if it's by any case contains a code injection, then you are not monitoring it, you can get reproduce such scenarios of attacks. And there is a common saying, with great power comes great responsibility. So here you have no power almost. You're counting on Amazon, Google, Microsoft, they have the power on the server. But still, you have the responsibility. You have the responsibility to keep your code well secured and monitor its deployed version. And how you do it, you, like code is code, as I said. You should scan it and use any other security tools to make sure there are no vulnerabilities in it. One way to use one tool is a SaaS tool. That's, as I said, you can download the code automatically with an integration from the AWS and scan it with every SaaS tool, in this case of checkmarks. And here we say a project that was predefined to be integrated with the Lambda project. The code is downloaded with the current version. You can trigger events that's only on update version, there will be such scan. The scan was finished. And code injection is a code injection. So the same queries and rules that are valid for regular code will be valid for this JavaScript code. The only difference is the input is not a common input in other functions, it's as an event trigger. And here in the checkmarks results, you can see how the event trigger go in the data flow till the code that's been run by an eval. And if you would scan the code, you can see this vulnerability, fix it, and upload the fixed version to the server. So the main research was of AWS Lambda. I reproduced all the following scenarios under some limitations and assumptions. There are two other commercial solutions. I did some small research about them as well. The code injection scenario, assuming the code is invalid in no sanitation, can be reproduced in every other solution. After all, code is code. The outbound connection and the default depends between vendors. In Amazon, the default was no VPC. In Google GCP, there is a firewall by default, but it's blocked only on common port, like the 50 port I use. It was being blocked, but I could do switches, and it was not blocking IP. In Azure, there is some more advanced settings of the Azure resources and how it's integrated with other tools of Microsoft. So again, there is some protection, but you should take the responsibility of setting it. The modify function code was not, I didn't succeed to do this in GCP since there was no SDK pre-installed. But maybe they will do it in one stage or another. And in Azure, it was not based on SDK, it was based on some common resources of the Azure that was accessible, but again, depends on the settings you're currently using. And the stored injection, modify other function code, was reproduced under the certain permissions in Amazon, but not reproduced not in Azure and not in Google, again, yet. They're all using still in beta and alpha version. Amazon is the most common and most stable solution, and the viral injection was reproduced, again, under the same assumption in Lambda. But it's not about comparing AWS, Google, Azure. It's about keeping in mind that the fact that you're using someone else's solution that will provide you the server, even if they are temporary, some damage could be done, and you should be responsible of your code. And that's it. Any questions?
Do you have any questions?
Does anyone have any questions they would like to ask?
Hey.
Quick questions. You showed that you were basically able some arbitrary stuff. Do you know some other kind of vulnerabilities that could be actually exploited in this scenario?
You can reproduce an SQL. Code injection was the most easy to reproduce. But if the original code was containing the SQL injection and there is a path, data flow from the input to the database call, in this case, it usually will be a serverless database with cloud resources. And if it will have access to a malicious input, it will be reproduced as well. After all, code is code. And the same for the protection, of course. The same rules that are valid for the scanning in checkmarks of tools, scanning tools that scan and find vulnerabilities in regular code are still relevant in the serverless world. More questions? Okay.
Thank you very much.